Now, the main problem with batch gradient descent is the fact that it uses the whole training set to compute the gradients at every step. And in particular, when you do this update, you have this whole training set XX that you're using. And for a large training set, this will be exhaustive. So the more rows you have, the more time this is going to take, right? Now, at the opposite extreme, stochastic gradient descent just picks a random instance in the training set at every step and computes the gradients based only on that single instance. Now, obviously, this makes the algorithm much faster since it has very little data to manipulate at every iteration. It also makes it possible to train on huge training sets since only one instance needs to be in memory at each iteration. On the other hand, due to its stochastic or random nature, this algorithm is much less regular than batch gradient descent. Instead of gently decreasing until it reaches the minimum, the cost function will bounce up and down, as you can see, decreasing only on average, thus the name stochastic. Over time, it will end up very close to the minimum, but once it gets there, it will continue to bounce around, never settling down, as you can see over here. So once the algorithm stops, the final parameter values are good, but not optimal. Now, when the cost function is very irregular, this can actually help the algorithm jump out of local minima. So stochastic gradient descent has a better chance of finding the global minimum than batch gradient descent does. Therefore, randomness is sometimes good to escape from local optima, but bad because it means that the algorithm can never settle down at a certain position, including the global minimum. One solution to this dilemma is to gradually reduce the learning rate. The steps start out large, which helps make quick progress and escape local minima, then get smaller and smaller, allowing the algorithm to settle at the global minimum. This process actually has a name. It's called Simulated Annealing because it resembles the process of annealing in metallurgy, where molten metal is slowly cooled down. Now let's implement stochastic gradient descent with a variable learning rate. And actually the learning rate will be set to the learning schedule. That means that we've got, instead of iterations, now we'll call them epochs. So we've got 50 epochs, and we'll define a starting and ending point of time. Let's set them to 50, 5 and 50 respectively. And let's define the learning schedule. So given time t, I will return t0 over t plus t1. So as we did previously, let's initialize using a standard normal distribution the value of theta. Then at each epoch, I'm going to pass over all the m times, where m is the number of features, and I'm going to pick a random index, right? Because we said that stochastic gradient descent picks a random data point. So let's pick a random index and let's extract the corresponding index as such, also the corresponding target value as such. Now let's compute the gradient. So as we did previously, the gradient was updated as follows. Right now, since we extracted xi and yi, then instead of xb, I've got an xi, right? And instead of a y, I've got a yi, right? And furthermore, I'm going to compute an eta that is according to the learning schedule. I'll pass it the current time, that is epoch, and update the time based on the counter right here, right? So at a given I, this increments, but within the window epoch. So now let's update our theta using the same exact equation as gradient descent or batch gradient descent. So right here, and there you go. So now let's do the plotting. Let's run this and let's see the value theta. And there you go. I got a 3.26, 1.69. But pay attention, if you run this again, you're going to get different values because you're randomized, right? And it depends on the randomized strategy that was taken at this particular instance of the simulation. That said, let's go ahead and do some plotting. So I'll plot the data points in dotted blue. I'll label the X and Y axis as such, and I'll show my plot. There you go. Now let's go ahead and plot over here what's going on within the algorithm, right? So over here, let's go ahead and predict the line as we did in SGD. So when you're less than 100 iterations, you do some plotting, except for the first iteration, which is plotted in red, right? So I'll need all this block of code. I'm going to reuse it exactly the same, right? So over here, like this. But I've got an I over here, so let me set epoch equal to 0 and I less than, I don't know, something like 20, right? So first we perform the prediction. Of course, the prediction is performed using all the data set, but the update is only using a random data point. And instead of iteration, I've got the I index, right? And there you go. So as you can see, we didn't do a pretty good job. And the reason why is because my eta is, I think it's still from, it's really small. So in gradient descent, the problem comes from here. We're still dividing by m, but m, okay, now I get it. So m in this case is 1, right? Because you're only picking one data point. So setting this to 2, I think this fixes it. So there you go. There you go. Okay, so now that instances are picked randomly, unlike previously, some instances may be picked several times per epoch, right? So we might pick, let's say, the 6th data point multiple times due to the randomness over here, right? Now, if you want to be sure that the algorithm goes through every instance at each epoch, another approach is to shuffle the training set, then go through it instance by instance, then shuffle again, and so on. However, this will slow down conversions. To perform linear regression using SGD, we can also make use, instead of you having to write down the code as I did over here, you can use the Scikit-Learn to run SGD. And in particular, let me show you right here. So from sklearn.linear model, we're going to import the so-called SGD regressor, right? We're going to instantiate an SGD regressor as such, define the number of iterations, let's say 50, penalty, let's set it to none, and the eta. So eta node is the beginning, is the start point, right? Notice that eta changes per iteration. So eta node will serve as a starting point. And notice that once you specify eta node equal to 0, this means that we start with a learning rate of 0.1. Now the learning rate used over here is the default learning rate. It's different from this one we have over here. And also it does not use any regularization right here. So, and the penalty equal to none, it means that we're not using any sort of regularization. So let's fit. So fit x on y as such. Running this, actually it's not n iterations, I think it's max iteration. And there you go. Okay, so let's see what we got. Let's see the intercept. It's 4.59, so this is theta 0. And let's see the other coefficient. It's 2.96. That is a solution that is very close to the one returned by the normal equations. Not as good, but close. So with mini-batch gradient descent, it's really easy to understand mini-batch gradient descent once you know the concepts of batch and stochastic gradient descent. Here, at each step, let me show you how we can implement it, and I'll explain it on the way. So let's save the path taken so that we can animate the plot and define number of iterations, say 50, and a mini batch size, which I will explain just now. Let's set a certain seed, let's say 60. And as always, let's initialize a theta to be random. As we did in batch, let's define the starting and ending time points, 200 and 1000 for the epoch, and define a learning schedule as we did previously. So as such, we will return t0 over t plus t1. So as of now, it looks like a stochastic gradient descent, right? Let's initialize time to 0 and run over epoch as such. So in mini batch gradient descent, at each step, instead of computing the gradient based on the full training set as in batch gradient descent, or based on just one instance as is the case with stochastic gradient descent, mini batch gradient descent computes the gradients on small random sets of instances called mini batches. So it's in between stochastic and batch, right? So we're picking small chunks or mini batches, as the name suggests, of the training set. So we're going to loop over mini batch sizes as such. And at each iteration, we will increase t and pick a mini batch as such, of size mini batch size, which in our case is 20, and its corresponding yi, right? We'll compute the gradient as we did in the stochastic. So I'll be picking this guy over here. But be careful, your m is not 1, it's now mini batch size. So since you're picking that many data points, then your m is that much. And then you update eta according to the schedule, according to the learning schedule. Then finally, you'll update theta as we did with all the previous gradient descents. So you'll descend by an amount of eta gradient. And since we're going to animate the plot, then I'm going to save it in theta. Each value theta, I'll just save it in the vector theta by just simply appending the value of theta. Now it is worth noting that in mini batch, to randomize stuff, some shuffling happens before updating theta. That said, right here I'm going to shuffle the indices. So shuffled indices as such, then I'll create an XB shuffled, that is as such, and likewise Y shuffled. So we're just shuffling before picking the mini batch window, right? And right here I'm going to pick from the shuffled. I'm going to pick the mini batch from the shuffled vectors instead, right? So running this is it runs properly. Now let's take a look at theta. There you go, pretty close to 4 and 3, right? Now let's plot the path taken by mini batch, right? So for that, first let's cast this as an array, which will turn out to be useful as such. And for animation, I recommend you to write the following line of code: matplotlib notebook as such. Now for that, I'm going to import animation as such, and I'll define an x vector that is the first column of this vector. It's the first column, and the y component is the second column, right? So Let's define a figure and an axis, subplots as such. Then let's plot the path taken as a normal path with no animations till now as a green line with plus signs on each theta point. Set the line width to be narrow, so set the line width to 1 and we'll label it as mini batch. Now I'm going to move a red dot. I'm going to animate a red dot. So my red dot is going to start at the first X point and the first Y point, right? As a dotted red. So this is what you see right now, no animation. This is the path. The green path is the path of mini batch and the red point is the initialization point. Now to animate the point, to let it walk on this path, all we need is a function, a callback function that will set the data of the red dot. So set data, right? And each time I'll pick the ith index of vectors x and y. And I'll return the red dot. Finally, I'll create my animation using the func animation, pass it the figure, the callback function, the interval of animation. I'll set the frames to be 1000, even though 60 is enough, I think. I'll set blit to true. See what's going to happen. There you go. So if we zoom in over here, you can see how the thing behaves, how mini batch behaves, right? Stop this. Okay, so this is it for mini batch. This is how it works. So we're picking a mini batch, as the name suggests, from the training set. And we can see that it wiggles, but not as much as Stochastic does. Well, okay, let's give an X label for now. So plot the X label, and let's label the Y axis as theta 1. Now let's make use of the functions we had previously over here to save, let's say, the stochastic gradient, right? So right here, I'll create an empty vector, which I will be filling up at each iteration of stochastic gradient. So all I have to do is just append the value of theta. And before running it on this animation, I'll have to cast it as an NP array as such. So this is the stochastic gradient descent path of theta. So we go back here, run this, should be saved by now. Okay, let me run this block of code. Okay, now let me here, instead of, actually let me copy paste this code and run the same guy over here. Instead of M, I'll put an S, and over here I'll type in stochastic, right? So this is how stochastic gradient is working. And if we just zoom in here a bit, we can see the wiggling going on over here, right? Actually, the guy is not working because, let me delete this, because we still have the callback function over here, so it's not good to have the same callback function. So I'll call this animate2 SGD, and I'll name this as stochastic. And there you go. You can run this at the same time. So you can see how stochastic gradient descent works. Now let us go back to batch gradient descent, right? And do the same thing as we did. That is, over here, let's define a batch gradient descent that is empty, and at each iteration I'll just append theta, right? So running this, there you go, we have the vector, and now casting it as an NP array. And finally I'll just copy paste this code over here, and the X and Y values are the batch gradient descent. So there you could see how linear it is. Actually, let's fill in another path. Let's fill in the path over here. So batch gradient descent, and at each iteration you will append theta. Let me comment those guys out because I only want the guy corresponding to 0.1 because it does well. Let me set this guy to, and there you go. We have it right now. Okay, so now let's increase the number of iterations and see what happens right here. Going back down here, and there you go. This is the path taken by the stochastic gradient descent. There you could see how it approaches and how it becomes more accurate, right? Come on. See how clean and accurate it is, right? Good. So, in contrast to batch gradient descent, this is how stochastic gradient behaves, and this is how mini batch behaves, right? So in the extreme case where the mini batch size is 1, you get this. So this is like a shuffled version of stochastic gradient. It's really randomized, but it goes really close to the global minimum. That is 4/3, right? It goes close, but it never settles down. Increasing the batch size, let's say 100, this is what you get. A behavior very close to batch. So as the mini batch increases in size, 100 is the maximum. So as the batch increases in size, mini batch is actually batch, right? Because the mini batch size is the total number of training set, and hence you're not making full use of stochastic. Actually, you're not using stochastic over here. Other than the shuffling part, there's no stochastic gradient descent going on, right?